The other thing I wanted to ask you guys is Wednesday a good day for our tutorials? Pardon me? During Flex? Is that problematic for anyone in particular? Yes? I think we talked already, right? Okay. Is there a day that is better? Like is Tuesday a problem for anybody? We could move it to Tuesday. Yeah? Any complaints about that? Okay, and you guys are the only ones who are here, so I'm going to say you're the voting people. So yeah, Tuesday it is. Yes? It'll be every week and hopefully we'll just get done sooner. Yes? And if it's like, if you guys let me know in advance, if you're like, we all have like a bunch of tests this week, we can make arrangements for it to be like not that week. Do you know what I mean? Like, let me know. Okay? Plus, they will be recorded, so we'll be good. Okay, so gas laws. These are all pictorial. Page 15. So, and did you want one? Oh, nice. Okay. So you'll notice that what is staying the same between these two? This, by the way, is a pressure gauge. Pressure. So P1 equals P2. That is staying constant. What are we changing here? We increase the temperature. And what happens to the volume? The volume increases. And so we can say that volume is proportional to what? Temperature. So if we were to write a formula for this, we would say when two things are directly proportional to one another, we would say V1 over T1 equals V2 over T2. Is good? When things are directly proportional to one another, it means that if one gets bigger, the other gets bigger. So let's say this would be bigger over bigger. So it remains the same as before. Yes? Okay. I don't know whose law this is. I don't really care. You don't need to name the laws. You just need to understand them. Yes? Okay. Now we have, let's make sure that the sound is recording on this thing too. Yes, it is. That's good. Okay, so now we have an immovable piston. We have pressure 1 and pressure 2 are not the same. What are we changing? What are we changing? Are we changing the pressure? What have we done? We change the temperature. We increase the temperature. And what are we keeping the same? Yeah, volume 1 is equal to volume 2. And when we increase the temperature, what is changing in response to that? Pressure. So we change temperature and pressure also increases. That means, now how would we phrase this? Would we say that temperature is proportional to pressure, or would we say pressure is proportional to temperature? Which one? Pressure is proportional to temperature. You put your dependent variable first in a proportionality statement. So we would have P1 is proportional to T, or not P1. Pressure, just P, is proportional to T. So I would like you to write the equation that includes P1 and T1 and P2 and T2 based upon that and what you know about how these things work. So you're looking to do something like this, but for pressure and temperature. P1 over T1 equals P2 over T2, because if we make the temperature bigger, then the pressure also gets bigger. And so the ratio between the two remains the same. So for all of these, we have to be keeping everything constant except for the one thing that we are changing. So we kept V1 and V2 the same. We also kept N1 and N2 the same. What are N1 and N2? Number of moles. Okay, so those are things that are remaining the same. And also for the one above it, you'll notice that the N1, P2, P1 equals P2, and N1 equals N2. So all of these little laws depend on keeping stuff the same and changing one thing and watching the response of the other. Okay, what are we changing here? First of all, what are we keeping the same here? We're keeping temperature the same. Okay, you can see that's the same level. So T1 equals T2. Anything else? Number of moles. N1 equals N2. So those are the things that we're keeping the same. And what do? We do what? We change the volume. We decrease the volume, which causes what? Pressure to increase. So how would we write a proportionality statement for that? Pressure is inversely proportional to volume. In other words, pressure is proportional to 1 over V. And how would we write that as good morning, how would we write that as an equation with P1s and V1s? Yep, P1, V1. We're on page 15. Equals P2, V2. And what would that look like on a graph? If we graphed the pressure, who's the independent variable here? Volume. And the pressure, what would that look like? Yeah. Your inverse relationships look like that. What would the graph of the pressure-temperature relationship look like? First of all, which one would be on the x-axis? This is back on page 15. Temperature is going to be on the x-axis. That's what we're changing. Pressure is here. And that is a what kind of relationship? Linear relationship, direct relationship. And we could also go back to our other one here, and we changed the temperature. And how did volume respond to that? It went up. Okay. All right, so we got those ones. Let's see what else we got here. Next one, what are we keeping the same here? Temperature is staying the same, so T1 is equal to T2. Anything else? And are we? Ooh. Pressure. P1 equals P2. And it looks to me like what we have changed, we couldn't just change the volume and magically have particles appear. Although that's not entirely true. Next year, you'll find out that we can do that. Next year, you'll find out that if you have a reaction like this, you've got, this is a really common one. If you have 2 NO2 and it is in equilibrium with some N2O4, what can happen is if you increase the volume, it will produce more molecules to fill up that space. Right? So what'll happen is some of the N2O4 will break down into 2 NO2s, which will increase the overall number of gas molecules. Did that make any kind of sense? And if it didn't, that's okay. Yes? What it's doing is it actually has to do with collisions. So why don't we just leave that for next year? Okay. And we'll say in this case, maybe if we added more, if we increase N, then volume will increase. And we'll put over here in Chem 12, if we increase volume, then N will increase.
So N is the number of moles of molecules?
Number of moles of molecules, okay? But we'll leave the whys and hows of that for next year, but we'll just kind of put that as an aside. Okay? So we can say in this case that volume is proportional to N which means that, what would our equation be? Let's put N1 here. Is V1 going to go beside or below? Below. N2, V2. And our graph would, of course, look like this, no matter which way we draw it, no matter which one we make the dependent variable. Is that good, Victoria? Yeah? Okay. So I could probably leave this to you to fill in. Do you want to try it on your own? Just do that real quick. So you're looking for directly or inversely? And what I want you to do is, rather than looking back through your notes, I want you to think, if I increase, what happens to P? And that'll tell you whether it's directly or inversely proportional. So think it through. If I increase the volume, what's going to happen to my pressure? You can write in there, by the way, if you want to. So you can check your first one. Let me know if it's not making sense. If you're like, I don't understand why. Don't just be like, oh, I'll copy it down. It'll be okay. Are these making sense? Yeah? Okay, good. Because then we're going to take them and we're going to put them in the combined gas law, which is always fun.
Does it matter which way you like them, what I like?
No, you can put them top, bottom, or upside down. Good question. Yeah? E equals nRT. Okay, now the combined gas law, I have to figure out how this goes again. P1, V1 over N1, T1. P2, V2 over N2, T2. Let's see if they were clever enough to put that in our data pages. I don't think they were, but let's just check. Oh, hey, there it is. They didn't put in N, but they do have P1, V1 over T1 equals P2, V2 over T2. So if you ever want to, you can just use this. And if you're like, I'm keeping temperature the same, that tells you that P1, V1 is equal to P2, V2, and you can just get rid of the temperature term if you're keeping temperature the same. Okay, or if you're keeping volume the same, you can just cross out the volumes, right? Because if they're staying the same, you can just ignore them. So P1 over T1 equals P2 over T2. And same thing, if you keep pressure the same, V1 over T1 equals V2 over T2. And N just would fall at the bottom. I'm not quite sure why they don't include the N, but they don't. Pardon me? It doesn't matter. You're often keeping the moles the same anyway, so often it does not matter. Okay. No, I don't want that one. Here we go. Okay. Now the ideal gas law is very, very similar. It says PV equals nRT. And everything looks familiar except for the R. R is the gas constant. And being a constant, it is constant. And if you look at PV, if you solve it for R, right, if we leave R over on that side by itself, PV over NT is equal to R, and R is a constant. And guess what? P1 V1 over N1 T1 equals P2 V2 over N2 T2, which means that that is a constant, right? So what is that constant? Again, on our data pages, we can look and we can see they have given us a couple of values. All right, they've given us one that is in joules per mole Kelvin. Don't forget, -1 means per mole per Kelvin. But the one we're going to be using is 0.08206 liters times atmospheres per Kelvin per mole. Yes? That's the one we're going to be using because we are using volume, liters. We are using pressure, atmospheres. We are using Kelvin, temperature, and we are using N, moles. So that's the one we're going to use. The other one comes into play when we are doing stuff with electrochemistry, because electrochemistry has to do with energy, the voltage, the joules per coulomb. Okay, but that will be at the end of grade 12, so, or the AP Chem 12. So don't worry about that other R. We're just going to be using the one with liters and atmospheres. Okay? There we go. And there are some questions which you can do should you so desire. If you feel like you have a good enough understanding of this as it is, you don't have to do them. There we go. Let's go now to the ideal gas law, which is on page 19. See if you can remember from our discussions last week. Was it only last week? Holy mackerel. Feels like forever ago. An ideal gas is one in which the molecules occupy no space. So if you had to think of all the various gases, can you think of one that might be the most ideal in that it takes up the least space? Hydrogen is a good one. Helium is another. Okay, so hydrogen and helium tend to be the most ideal. Since they are the smallest. And they also have something to one another. I'll give you a hint. This word's no. No attraction. So again, who would be good candidates for having very, very little attraction to each other? Hydrogen and helium, right? Because they are nonpolar, so they don't have dipole-dipole forces. They only have LDFs, right? And they're small, so their LDFs would be minimal. Yes? So He and H2 are the most ideal. They only have LDFs because they're nonpolar. They have a small number of electrons, so they're not very polarizable. Therefore, the LDFs are small. Water is small, but it's got those hydrogen bonds, which make it kind of sticky. So it would not be super ideal. Yeah, that's basically it. When things get really unideal, they start turning into liquids. Okay. Now, do you think gases would behave most ideally at high temperatures or at low temperatures? I want you to think about that. You've got molecules passing by one another. Are they going to behave the most ideally? In other words, which one will result in the either smallest size or the least attraction if they're moving quickly or if they're moving slowly? Let me give you a hint. It's not about size because molecules do not change size. In which case would attractive forces be the most meaningful? When particles move like this or when they move like this? When they're moving slower, because you can imagine if they're moving slower, it's like they'll start to move towards each other and there's not really a chance for them to escape that attraction. Whereas if they're moving quickly, they're like, yes, I was attracted, but I was moving that way fast, so I just like kept running. Yes? Okay. So only at what type of temperatures? High or low? High. Oh, hang on. No, I'm doing it backwards. I'm doing it backwards. Oi, oi, oi. My pen is not working. My brain is not working. Oh dear. Oh dear, oh dear, oh dear. Okay. Only at low temperatures do we see significant non-ideal behavior. Okay, so non-ideal. What do you think about pressures? Pressures, the best way to increase pressure, you can do it by increasing the temperature, but that's going to result in you having a high temperature. So how else can we increase pressure? We can take the volume and squish it. So if we're increasing pressure, is that going to result in a more ideal gas or a less ideal gas? It's going to be less ideal. Why? Because they're closer to each other, so the IMFs become more significant. Also, if the space is smaller, proportionally, the molecules will take up a larger percentage of the space. So you can't say, oh, they take up no space. So if we had a larger volume, and we had 1, 2, 3, 4 molecules, we could take those molecules and shove them down in one corner to see how much proportion of the space they take up, yes? But if we take that at a smaller volume, you can see now they take up more of a percentage of the space. It means they're just going to be closer to each other, so they're going to have more intermolecular forces, okay? So only at low temperature and high pressure do gases show significant non-ideal behavior. We call these our real gases, therefore, would exhibit ideal behavior they would act ideal at what type of temperature? High temperature and low pressure. And hopefully that just makes sense to you. But if you forget, we have a little mnemonic device for you here. We have this peasant woman out plowing the fields. And what's going to be useful for that? She needs to have strong thighs so she can push that plow. Yes? I relate to this because I have always, even when I was 11 years old and like just a tiny little person, my thighs were still they used to call them thunder thighs back in the 80s. And I always had thunder thighs, no matter how young, no matter how skinny, always had thunder thighs. And that's because I can go back to that strong peasant, Western European peasant stock, right? I'm like, let's take the plow. Okay, anyway. So it is ideal for a peasant to have strong thighs in order to plow the field. All right, we have a little picture there. So gases are most ideal. It is ideal when the temperature is high, phi, and when the pressure is low, plow. Okay? I feel like that's one of my ancestors there. I don't know. Okay. For now, we'll consider only ideal gases. We'll worry about real gases way down in 13.5c. Okay, so we're not going to worry about them until the very end of this section. The ideal gas law, of course, it will be in your data pages. Where is it? Here it is, PV equals nRT. It is in the gases, liquids, and solutions section. But apparently on the AP exam, now that it's online, you have to you have to pull up your equation sheet on the same screen. And it's going to be like a laptop screen, so it's a little awkward. So if you just know PV equals nRT, then you don't have to look it up. And how can you remember it? Many people call it the pervert equation or the perv-nert equation because it helps them remember it. PV equals nRT. Yes?
Do you have periodic table online?
Online, which makes me sad. But chances are you won't need to use it that much anyway. They often do things like give you molar masses if you need them. That's the only thing I can think that you would probably need it for, other than maybe like knowing the number of valence electrons in something. Yeah. Okay, so here we have our R values. They used to give us this one, but apparently they don't give us this one anymore. So we can just cross this one out. Let's just make sure they don't. Haven't updated my book yet. Oh, not that one. There we are. R. Nope. So you won't have to worry about that one. If you decide you want to write it into your own book, you can. Torr and millimeters mercury are equivalent, so you can use it. I probably have some problems that use this value, so you might just want to like write it on the cover of your gas booklet or something like that so you have it handy, because it's not handy on your data sheet. And I don't know if you have your data sheet with you today. It's probably not convenient for you to access. Anyway, temperature has to be in Kelvin. It will not work if it's not in Kelvin. So Celsius, you must convert to Kelvin. Does anyone remember how to convert to Kelvin? Plus 273. Okay, so 0 Kelvin is equal to negative 273.15 degrees Celsius. And because the degrees are the same size, 273.15 Kelvin is equal to 0 degrees Celsius, which means, and that is also on your data pages. Excuse me. It doesn't tell you that that's 0 degrees, but you know that STP is 0 degrees Celsius, right? So if you forget that, there it is for you. If you are given a pressure in kilopascals, you must convert kilopascals either into atmospheres or torr, so you can use the given R values, but we're going to cross out torr because it's no longer in the data sheet. AP is not going to give you, I don't think, they're going to give you kilopascals? No! They're not going to give you kilopascals because it's not on their sheet. Okay? This is maybe a little out of date because I didn't update this particular page with the new thing. I have to go through and fix that, but that's okay. Anywho. Huh? Kilopascals is just not there. The R value in torr is just not there anymore. Okay, so this is now gone. Okay, so we only have the liter atmosphere per mole Kelvin. I don't know why. Whatever. This one is gone. And I need to update. Update. And apparently it's laid out differently online than it is on the printout copy, but like you can click on like gases and solutions. There'll be like a thing where you click on gases and solutions and it'll come down with the gases and solutions. You will be able to practice all these things as soon as we get onto AP Classroom, which will be available to you in September. Maybe the very end of August. We'll see. We'll see how quick we can get up in there. And you can then practice using that. Okay, so here we have using the ideal gas equation, and you are going to use your new periodic table, which has 2 decimal places for the 2 decimal places for the masses. So let's finish one of those. I'll make sure I post this online as well. So if you just want to go, give it a try. I'll give you one of these on a colored sheet of paper like later, but this is what I happen to have around. Yes.
So you're all gonna get is this and then on top of those.
Yes, but that's for AP stuff for Chem 12. And when you take Chem 12, you'll be writing the regular Chem 12 tests. You'll get like the whole Chem 12 data booklet, which has a normal periodic table with 1 decimal place, and it's got table of acids and polyatomic ions and all that sort of stuff. Yes. It is, the multiple choice section is digital, but you will be writing your answers in a written book because it's really hard to write chemistry stuff. Like, honestly, subscripts, superscripts, arrows, blah. Yeah. No. Oh, this is confusing. I have to actually read the question. Oh, interesting. See why this question is tricky? It looks like it gives you a volume, right? And you're like, oh, I got volume, got temperature, pressure. But it's it holds liquid, and the ideal gas law only applies to gas. So that 5 liters is just a red herring. Yes? This 5-liter tank holds 3 kilograms of propane. So you can use your 3 kilograms to find the moles of propane, C3H8. But your actual volume, it says what volume would be needed to hold the same amount of propane as a gas. Is good? And then we can use, we now have our N value, we have our T value in Kelvin, we have PR is equal to 0.08206 liter atmosphere per mole Kelvin. And so we can do PV equals nRT. Do your solving first. So solve for your unknown, which in this case is V, because you don't want to be moving around something like 0.08206 liter atmosphere per mole Kelvin. You don't want to have to write that more than you have to. So do the solving first. So V is equal to nRT over P. And then you start plugging things in. You've got your N value, 68.036 moles times 0.08206. Do you need to write this whole unit out? Yes, you do. Liter atmosphere per mole Kelvin. Yes. Because that's the value you're given in the data booklet, but your sig figs would still be here because you have the 25, right? So the 5 is your uncertain digit. So when we add, we go to the first uncertain digit, which is in the ones position. Yes? So when you're doing temperature, you have to watch out for that. And then our temperature is 298.15 Kelvin over our pressure, which was a nice number, 3.0 atmospheres. That's probably going to be our least number of sig figs anyway. Yeah, we've got 2 sig figs there. Check and see, do your units all cancel out? Moles on the top, moles on the bottom. Atmospheres on the top, atmospheres on the bottom. Kelvin on the top, Kelvin on the bottom. And what are we left with? Liters. Hallelujah, that's what we wanted. Okay, and you just plug everything in and we get what we get. So I don't know. Let's plug it in. 68.036 times 0.08206 times 298.15 divided by 3 equals 554.9 liters, which is going to then round to 2 sig figs, which is going to be 550 liters. Other than the fact that reading the question is a little tricky, like what's that 5 liters doing there? Remembering to change your temperature into Kelvin. Do be sure that you write all your units in your work. I know it's a pain in the ass. Do it. They ask for it. The Chief Reader's Report, the one where they say what students should look for and try to do in the future, write units in your work. Okay? Now, we also have density. We're not going to get to stoichiometry with this because we have to do gas densities and molar mass. Do you remember how we used to go from density to molar mass and back and forth when we were just at STP. How did we do it at STP? What did we use? The grams stay the same, but we need to interconvert between liters and moles. And what did we use when we were at STP? 22.4 liters per mole. So that was easy enough, right? But now we won't be at STP. At non-STP, you're going to use the ideal gas law to interconvert between the liters and the moles. So it's a bit of a pain. So let's just review for ourselves. What is the density of carbon tetrachloride vapor at STP? And this is probably all we'll have time for today because I want to get you out of here by noon. Okay, so we will just do this and then we'll leave whatever we need to for next day. Okay, which will be next Tuesday. Okay, during flex. So see if you can figure this out. Is it 22.4 moles per liter or 22.4 liters per mole? 22.4 liters per mole. Is good? Okay. And just to be clear about because we've only got like, 25 minutes during flex time. I'm going to start like at 8:35 on the dot. So be here at 8:30. We'll start at 8:35 on Tuesday. And if you come in late, that's okay. It'll be recorded, right? But I will be starting at 8:35, bam, on the dot. So if you're a person who likes to be there on time, then bam, be there on time. I will start exactly at 8:35. Okay? And if you're like, I don't care, it's okay, I can catch up on the recording afterwards, I'm okay with that. Just come in quietly and make yourself at home. Okay? Excellent. Thank you guys so much for coming in on your week off, quote unquote. I know some of you have been writing assessments and stuff, so not so much off.
Not my week off.
Not really a week off. No, I know. For me, neither. I've been writing report card comments all week. Thank you.
Thank you.
Oh, and you can keep the pages that you wrote on. Okay. That way you can just, pop them into your book or whatever. Yeah.
Thank you.
Good stuff.